Good morning. It's a pleasure to be here, and it's a great pleasure to introduce the program that I've been working on, 3D dimensional SoC work. So the purpose of the 3D SoC program, that stands for three-dimensional monolithic silicon on a chip, system on a chip, excuse me. The main goal for this whole program is to develop novel monolithic, which I'll describe in just a minute, 3D fabrication technologies. And the important reason for doing this technology isn't because it's really cool, but it is to enable new architectures that drive a greater than 50x SoC performance at power. And the important thing to realize is that this is a 90 nanometer technology where we're implementing this technology, or 90 nanometer dimensions, and that our comparison for 50x is 7 nanometer 2D technology. For those of you that say, well, wait a minute, do you have magic sauce or something? You heard earlier from Wei Chen where he talked about the fact that most of the effort that was spent in their chips was spent going to and from memory. You've heard that several times. The main advantage of this technology is it potentially provides up to 4 gigabytes of memory on the actual die. And this is monolithic, and when I say monolithic in this particular case, I mean developed in a single integrated die stack. It is not wafer stacking or packaging. It is actually a monolithic process, fabrication process that occurs. So our specific goals around beyond that 50x are to develop interconnect densities that are greater than 9 million interconnects per square millimeter. Typically in TSVs, that's on the order of 3,000 per square millimeter. And that is possible because the interconnect dimensions that we're talking about are back end of the line interconnects at 90 nanometer. Typical pitches are on the order of 300 nanometers. Interconnect bandwidth that's associated with those interconnects up to 45 terabits per second, as opposed to typically what would happen even in advanced systems is on the order of 1 terabit per second. This is internal interconnects inside the die stack, but remember it's going to 4 gigabytes of memory. And then on-die memory access energy of less than 2 picojoules per bit, as contrasted with something on the order of 32 picojoules per bit for off-die memory access. Remember, the important thing is that we have large amounts of memory and large amounts of logic all connected in this integrated monolithic stack. The other goal is to make sure that this is done at yield. And you'll see that, that one of the partners here is Skywater Technology Foundry. They are a production fab, and they actually can make this, they need to be able to make this at yield. And we recognize that to do three-dimensional design requires a new set of EDA tools. So in addition to the fabrication technology, we're funding a separate set of researchers to look at the design tools that are necessary to build truly three-dimensional monolithic systems. And the other goal for this is to have it all fabricated inside of a foundry that exists here in the United States. So what's happened? The program has been going for roughly a year out of a 3.5-year program. So first one is carbon nanotube FETs and resistance memory ReRAM have been fabricated at Skywater Technology Foundry. The reason that we're using carbon nanotube FETs is because they can be fabricated at low temperatures. One of the big difficulties in building up a monolithic IC is you have to fabricate the technology for the transistors, and it has to be compatible with back end of the line technology as well, which means it needs to be fabricated at temperatures below 450 degrees centigrade. Standard CMOS, that can't be possible because you do doping and you have to build single crystal silicon, and all of that requires high temperatures. In the case of carbon nanotube FETs, this can be done at a low temperature, as it can be for resistance RAM as well. And carbon nanotube FETs and ReRAMs have been built at the foundry. And there's key carbon nanotube FET building blocks that have been demonstrated at MIT, who was one of the other performers. They built complex digital ASIC that's been fabricated with CN FETs, as well as having multi-level CN FETs constructed on the same wafer. And finally, we have a calibrated process design kit which has been developed and delivered to alpha design teams. All of this is on a technology which is very novel and unique. The performers that we have here, you'll be hearing followed up with a deep dive from Max Shulaker from MIT, who is the principal investigator. He has been driving the CNFET development. Mark Nelson at Skywater has been driving the 3D SoC fabrication and yield enhancements. And Subhashish Mitra and Simon Wong at Stanford have been working on system simulation to prove out that architecture and what kinds of architectures would get what kinds of performance improvements, as well as doing the ReRAM memory design, or ReRAM memory development. At Georgia Tech is the prime for the design tools. Professor Sung-Kyu Lim at Georgia Tech is developing the 3D logic design. Saibal at Georgia Tech is working on memory design development. And Krish at Duke has been developing design for testability, because at the end of the day, this whole technology needs to be testable, and needs to be testable in new ways, because there are new failure modes that will exist between the tiers of designs. Remember, the whole purpose for this is to enable new kinds of architectures that will take advantage of this monolithic access to large amounts of memory and distributed logic. And with that, I will turn the time over to Max to go into a detail on the development.
Alrighty. Thanks for the kind introduction. There we go. I want to begin by thanking DARPA, and particularly our program manager, Dr. Linton Salmon, for the support and guidance on this ambitious 3D SoC program. It truly is, sorry, let me back up here. Okay, it truly is both an honor to be able to speak here today, and I'm excited to be able to share with you the progress that we've been making over the first year. So I want to kick things off with some broader motivation. So we all know that electronics make the world go around, so to speak. And with the exponentially growing availability of big and abundant data, which is being generated constantly from the trillions of sensors, which will soon be connected across the Internet of Everything or the cloud, it's clear that electronics have the potential to continue to have a dramatic impact in all of our lives, with applications that range from genomics for personalized healthcare to building smarter cities to the military, science, finance, security. The list really is endless. And while it might seem that such a broad range of applications share very little in common with one another, they actually all share a very important common thread, which is that they all face the same challenge. And the challenge facing electronics today is that electronics is facing many challenges all simultaneously. It's the perfect storm. For instance, we've heard today about the power wall, which stems from the fact that as we shrink devices smaller and smaller, they no longer become more and more energy efficient. We've also heard of the memory wall, which refers to how a processor today can spend the vast majority of its time and energy just moving data around a system, from off-chip memory to the processor, back to the memory again, time and energy wasted not even doing useful computation. And the list of walls just goes on and on. So the question is, given all these obstacles, how can we possibly enable the next wave of computing? Well, today there exist two isolated approaches. On one hand, we try and create a better device, a new next switch. And while this is very important work, it faces some major challenges. For many of these new technologies, we simply can't build them yet. And even if you can give me a great device, there's a big disconnect between being able to make one good device and a billion with a B working devices required for VLSI systems today. And moreover, even if, and this is perhaps more important, even if you gave me the best transistor in the entire world, I'd still only see limited benefits for my applications, as the device-level inefficiencies themselves only account for a small portion of the total system-level inefficiencies. And for instance, the best transistor would not address the memory wall I spoke about previously. So a second separate way we try and improve computing is by creating new computing architectures, ranging from multiple processing cores to specialized accelerators. And while this is also very important work, it too faces challenges. There are only a limited number of design tricks we can play, and we play many of these already. And as we leverage complexity to hide inefficiencies, that complexity itself becomes a challenge, as design verification and design bugs are becoming increasingly dominant concerns and costs in chip manufacturing today. So I think it's safe to say that if we want to enable that next wave of computing, that business as usual is insufficient. As we heard from Dr. Chappell, that new innovations will be required. If we want to realize orders of magnitude benefits in performance and efficiency, then coordinated advances across the entire system stack, using new devices in order to realize new systems and architectures is necessary. Now, this is admittedly at a high level right now, so let's get a little bit more concrete. This is what a computing system today might look like. We have one chip where we do our processing and compute, a separate off-chip main memory, and these are connected through sparse, pin-limited physical interconnects. The dream and the goal of 3D SoC is to transform this into what you heard from Dr. Salmon, the following: a monolithic, three-dimensional integrated circuit where we have multiple layers of computing built directly on top of one another, all over the same starting substrate, so there's no wafer bonding required. These are interleaved with layers of memory, all densely integrated in this 3D stack through very fine-grained vertical interconnects, our conventional back-and-line nanoscale vias, which are orders of magnitudes denser than the through-silicon vias used today in chip stacking, truly embodying now computation finely immersed with memory. Yet despite the promise of such a future system, there's always a catch, right? And the catch here is that it's very challenging, if not impossible, to realize these new systems using today's conventional technologies. The processing temperatures for all these upper layers of circuits has to be very low, below 400 degrees C. If we go above this temperature, we can damage bottom layer devices and melt back-and-line metal interconnects. And this is particularly a challenge for today's silicon CMOS, which has processing temperatures in excess of over 1,000 degrees C for steps such as dope activation and annealing. So this is where we can and have to leverage these new emerging technologies to enable these new systems and architectures, as many of these new technologies can be fabricated at low temperatures, below 200 degrees C, well within our thermal budget. As I'll be speaking about shortly, for logic, we're using carbon nanotubes, and for memory, resistive RAM or RAM. But what I want to emphasize for you about this approach right now is that in 3D SoC, we really are getting the combined benefits now of using these energy-efficient, high-performing devices with these energy-efficient, high-performing architectures, which are naturally enabled by using these new devices to begin with. And when we can combine the benefits at the device and system level, the gains are substantial. So it's projected from my colleagues at Stanford that when successful, 3D SoC will be able to achieve over a 50x benefit in energy efficiency when implemented at a mature 90 nanometer technology node, compared against the best projections for 7 nanometer silicon CMOS chip implemented in 2D for the most challenging and impactful next generation big abundant data applications. So let's dig into some details here. If we want to realize these benefits and thus build these new systems, we need to use new technologies. And the technology which we're focusing on in 3D SoC are carbon nanotubes. So to make sure we're all on the same page here, a carbon nanotube, or CNT, is just essentially a rolled up sheet of graphene to form a nanocylinder with a diameter of around 1.5 nanometers or so. We use these carbon nanotubes to realize carbon nanotube field effect transistors, or CNFETs, where the CNTs act as the channel of the transistor with traditional lithographically defined source, drain, and gate regions, as I've drawn in the schematic here. So I want you to picture in your mind a chip with silicon SOI. Simply take out the silicon from the channel of those transistors, replace those with carbon nanotubes, and voila, presto, you got your CNFET system. Nothing else needs to change, though it can. So now that we have our CNFETs, you're probably wondering, well, how do you build these? So let me show you. So we start with any arbitrary substrate, and we fabricate these planarized metal electrodes to act as our metal gates. We cover this with our high-K gate dielectric, and then we uniformly deposit everywhere across the entire wafer these quasi-aligned carbon nanotubes through the solution-based deposition process that we've perfected. And this solution-based deposition is critical as it decouples the high-temperature CNT synthesis from the wafer we're building our circuits on, making the entire process of the CNFET fabrication low temperature, thus back-and-line compatible. We then etch out the unneeded parts of the CNTs, and then we fabricate our metal source and drain contacts, realizing the CNFETs. So once we have the CNFET, how do we realize CMOS, or complementary logic, using nanotubes? This has been a problem that's plagued the field and prohibited progress for well over 2 decades. But we now know exactly how to do this. The key was developing this joint two-step doping process. So first, we use work function engineering, where we use different metal contacts to contact our N and P-type transistors. But this alone is not enough. To be able to precisely control and tune the threshold voltage for all the different transistors in our circuit, we in addition use electrostatic doping, whereby we encapsulate different C and FETs with different oxides. And it's the type and stoichiometry of these oxides that allows us to finely control and tune the threshold voltage for the devices in our circuit. And thanks to this new process, we now have, for the first time, a wafer scale, robust and reliable, and silicon CMOS compatible process for realizing symmetric P-type and N-type C and FETs. All right, so you know what a C and FET is. You know how we make them. You probably have or are left with two burning questions in the back of your mind. So the first is why, right? Why did you have to pick something as hard as a CNT? Trust me, I ask myself this question every night before going to bed. The second question is, can you really make a chip using nanotubes? Because last time I checked, this was pretty far away. So let me take these both in turn. They're extremely important questions. The first, why CNTs? There are three reasons why CNTs are critical for 3D SoC. First, they naturally enable these new monolithic 3D architectures, which, as you heard from Linton, is the goal of 3D SoC, due to their unique low-temperature fabrication I just showed you. Secondly, it's projected that with enough hard work and engineering, a lot of which we've already performed, that a system made from C and FETs could achieve over a 10x benefit in energy efficiency versus the exact same system at the exact same node made from silicon FETs. And thirdly, and this point is more nuanced, but equally as important, we wanted to make sure that 3D SoC was not a one-time trick to get a one-time benefit. Rather, once 3D SoC is implemented at a relaxed, mature 90-nanometer node, then there's decades worth of future benefits to be had by relying on more conventional techniques for getting benefits, such as technology node scaling of the individual component technologies that comprise 3D SoC. So these are the three reasons of why nanotubes. What about the second question, which is, can you really make a chip using them? Well, if you asked me this question a couple years ago, it would be difficult to answer. The answer might have been no. But I'm very excited to say that over the last few years, and in very close collaboration with industry partners, we've completely reinvented how we manufacture this technology, transforming it from a technology that only worked in our academic labs to a technology that can and is already today working inside of commercial fabrication facilities as well as US-based foundries. And this has required innovations across the entire system stack, from innovations with low-level material synthesis all the way to innovations in high-volume manufacturing. And for the sake of time, I'm not going to go through all the details and techniques that we use, but I do want to highlight a few of the key developments that we've achieved over just this past year in 3D SoC. So in close partnership with our partners, at the very low level on the material synthesis, we've been able to now develop the purest solutions of nanotubes, both in terms of our ability to select just the good single-walled semiconducting CNTs that we want to use to build our circuits with, but also the ability to remove the bad contaminants out of the solution. In fact, these solutions are so clean and pure that wafers coated with these CNTs can and are already running today on the exact same equipment in the exact same labs that are manufacturing silicon product wafers. And this compatibility with existing silicon manufacturing infrastructure is extremely important when considering the adoption and feasibility of new technologies. A little higher up in the stack on the processing, I already showed you that we can realize C and FET CMOS with these new techniques. On the design side, there'll be some papers coming out in just a few weeks detailing some brand new design techniques that can ensure that a circuit will still function correctly even with the presence of any remaining imperfections left over in the CNTs. On the manufacturing level, I'm very excited to show you at the end of this talk that we've been able to achieve for the first time a C and FET CMOS process established within a US foundry. But ultimately, the proof is in the pudding, so to speak. So let me give you some concrete examples of how this maturity has matured rapidly over just this past year within 3D SoC. So rewind about a year ago, about 12 months, and we demonstrated the first mixed signal circuits built from CMOS C and FETs, like DACs, SAR-DCs, et cetera, integrating a couple hundred CMOS C and FETs. Fast forward just a couple months, and now we're integrating thousands of CMOS CNFETs, such as with this monolithic 3D imaging system, where we have multiple layers of carbon nanotube logic built directly over a starting silicon imaging substrate. So light comes into this chip, and then the carbon nanotube logic pre-processes on this data and then computes on it, transforming every single frame in real time from raw RGB values into highly processed information that's taken straight from the imager. Fast forward just a couple more months, and now we're integrating close to 10,000 CMOS CNFETs, realizing systems such as kilobyte size SRAM array, where we are able to yield the entire array using CNT CMOS again. And again, I'm excited to be able to share with you that we've now been able to realize the largest and most complex digital system fabricated from any beyond silicon immersion technology. This will be published in just a few weeks, so if you're interested, keep your eyes on the lookout for it, and I'll be happy to speak to folks offline in more detail as well. So I hope I've been able to show you so far both the promise and feasibility of a future CNT technology. But we have to remember that just a new transistor alone is insufficient. In order to realize the goal of 3D SoC, this fine-grained and dense integration of logic and memory, Stanford University has been pushing ahead and leading the effort on pushing the state-of-the-art of an emerging memory technology called resistive RAM, or RRAM. Now, there are many different emerging technologies for memories that could be used within 3D SoC, and many of these are being researched in other DARPA programs as part of the ERI. But RRAM was particularly well suited for 3D SoC, as it's non-volatile, can be fabricated at low temperature, and thus is seamlessly integrated in the back end, and has the potential for enabling multi-bit per cell storage for increased memory density. So let me give you some examples of some of the key progress that Stanford has made with this technology over the past year. So on one hand, in collaboration with CEA Leti, Stanford's demonstrated the first multi-bit per RRAM storage at the full array scale. And this was enabled by developing new systematic algorithms that ensure correct read and write operations despite intrinsic RRAM variability. Moreover, they were able to integrate this within actual hardware systems, in this instance, a non-volatile IoT edge microcontroller, where they used these multi-bit per RRAM cells coupled with very clever cross-layer optimizations, optimizing the weight encoding with this RRAM in order to enable actual benefits. In this instance, significantly improved inference accuracy for neural nets running on this actual chip. On the other hand, they've also addressed one of the key challenges often associated with RRAM, which is this limited write endurance. So they have this new technique called Endure, which they have proven in actual hardware and can prove mathematically can extend the lifetime of parts using RRAM to over 10 years in this instance. For more details on this, feel free to check out the poster and speak to any of the performers offline. We'll be happy to go into details. So while this progress with the CNFETs and with the RRAM is exciting and certainly very important, the most exciting part of this program is that we're actually transferring and building these technologies within a foundry today. So I'm going to spend the remaining few minutes of this talk going over our very close partnership and ongoing activities with SkyWater Technology Foundry. It's a US-based trusted foundry in Minnesota who we feel very fortunate to be partnering with for 3D SoC. So let me give you some details about the technology transfer into the foundry. As I mentioned, this is implemented at a relaxed, mature 90 nanometer node, as this simultaneously relaxes the device level requirements, still provides significant more than 50x benefits, and still also has future benefits that can be had by scaling to future nodes in the future. To date, we've been able to successfully establish all of the process modules within the foundry. I'm talking about the full CMFET CMOS process, the full RRAM process, as well as the full monolithic 3D integration of RRAM and CMFET CMOS within the foundry at SkyWater. And moreover, in addition to the processing advances, in order to enable all of you folks and the broader community to design your very own monolithic 3D SoCs using these new technologies, we've also developed the entire end-to-end design infrastructure so you folks can tape out your very own chips from the foundry as well. So let me give you some quick details on each of these points. So on the CNT CMOS, this is the first time we've spoken about this. We now have the full CMOS process established in the foundry Here you see a picture of one of the wafers from the first lots of the CMOS. Just like I showed you before, we have symmetric P-type, N-type CNFETs, and we're now progressing to fabricating larger scale systems and circuits, as you see in the SEM here off to the side. Similarly for the RM, we also have the RM integrated already within the back of the line. As you can see in this cross-section TEM, the RM is the blue and red, which is fabricated right in the middle of one of these nanoscale, very dense interlayer vias, bridging two metal layers. In this instance, I believe it's M1 and M2. And remember, just being able to build the devices is not enough. We also have the full design infrastructure so folks can tape out their very own monolithic 3D chips. And this includes, at the very bottom level, calibrated compact models to devices that are experimentally fabricated and measured from the foundry. It also includes a full commercial-grade process design kit, or PDK. And I mean it includes monolithic 3D design rule checkers, monolithic 3D layout versus schematic checkers, monolithic 3D place and route, monolithic 3D PEX extraction, and thousands of standard cells for designers to design and build their own systems with. And in addition, it also includes the full end-to-end design flow. So just like how you would design a 2D chip today, you start with your high-level description, like RTL, and this takes you through the entire process to actually getting your physical mass of reticles that the foundry uses to manufacture your chips. And it's very important for me to mention that this entire design flow uses the exact same industry-standard design tools that you're already using for fabricating and designing your 2D systems with very minor modifications. So now that we have the technology, we have the processing, we have the design infrastructure, we can actually start taping out 3D SoCs from the foundries. So what does that look like? Well, we build a bottom layer of CMOS using nanotubes. We do some of these dense interconnects. We can do another layer of CMOS, again using nanotubes. If we want to then build a layer of memory inside the stack, we do interconnects, and we put down first memory access circuitry, again using CNT CMOS, more interconnects, and then we end by fabricating this massive on-chip non-volatile main memory with the goal of integrating gigabytes worth of non-volatile memory within each of these 3D SoCs. And I want to end today on a slightly more special note to emphasize that these are not just some cartoons that look pretty in a PowerPoint. I've brought with, actually, a very special wafer. So this wafer was sent to me this last Friday, actually, just in time for the symposium. It was pulled out hot from the lot from SkyWater, and it's the first monolithic 3D IC ever fabricated within a foundry. So this wafer has on it already today RM, has on it carbon nanotubes, fabricated within this monolithic 3D stack. It's taken an incredible amount of work, an incredible amount of time, over a decade, to get from these cartoons to this wafer, but here it finally is. If you'd like to see it in more detail, feel free to find me after. Oh, all right. Thanks. I only have 1 minute left, so yeah. But feel free to find me after. I'll be happy to let you inspect it and check it out for yourself. So I want to wrap up with probably the most important part, which is acknowledging really the army of folks who have made reaching to this point possible. So it's been really a privilege of a lifetime to be able to lead this program at MIT with myself and the Dean of our School of Engineering, Professor Anantha Chandrakasan. It's really an honor and always such a privilege to work with folks who I will forever consider my own personal mentors, actually my PhD advisors. So Professor Subhashis Mitra at Stanford, as well as my co-advisor, Professor Philip Wong, and also a very close friend at Stanford, Professor Simon Wong. And also, we obviously are very fortunate and thankful to be working with the very capable folks at SkyWater Technology Foundry. That work there being led by Dr. Brad Ferguson, as well as Mark Nelson. And of course, I've left the most important people for last. And those are all the students you see off to the side. They are the true heroes who put in this heroic effort to make realizing these future systems possible. And with that, I'll wrap up. I hope I've been able to show you that 3D SoC is really transforming ideas into your reality. So with that, I thank you for your kind attention, and thanks.